So this video is about set theory for beginners, right? Or people that just need to understand the very basics of set theory, why we study it, right? And what are just the very rudimentary concepts behind set theory. You might need it to understand other fields, right? Like formal languages and automata theory. And really, it's the base. It's one of the bases of mathematics, right? So it's very introductory level video of basic set theory that you probably learned in high school or that you just need to brush up on. So this video may be part of a series that's later to come, but for now this is just a standalone introduction to set theory. So just an introduction to the concept of a set itself, right? What is a set? What does it mean? How do we interpret a set, right? It must be important if a whole branch of mathematics is named after it, right? So it's a very simple definition, right? It's a set is simply it's a concept that we all agree upon, right? So that we can build the greater mathematical objects, and it's not too hard of an concept to understand, right? So here I've shown a set pictorially as well, right? It's simply a collection of distinct objects, right? So a collection, right, an aggregation of objects, and this is intentionally vague, right? Because an object can be anything, right? It doesn't have to be mathematical. It can be an object. An object can be a living organism. It can be you. It could be a string of letters, as I've shown here. This is a set of strings. An object, a set is also an object. So set and object can really be anything, right? But a set is a collection of distinct objects. And so here I've drawn a set as a useful analogy, right? I've drawn it as some sort of container, right? This is a useful way to interpret what a set is. Some sort of box or container with some objects inside of it, right? And we can represent, this is just a visual way of seeing it, right? But we can represent this mathematically, like purely through the use of symbols, right? With curly braces, right? So this entire object is essentially equivalent to this container, right? You can see all the elements, we call them, of this collection, right? And so these two things are the same thing. And importantly, these objects in the set must be distinct, right? You can't have a set with the same object twice or thrice or 100 times. A set has to contain unique objects. Sets are also well defined, right? They aren't subjective. Well defined as in it's clear to understand and describe what is in a set. So here you can read over this example, a set of natural numbers from 1 to 10. That's very mathematically precisely defined. This is a well-defined set. What's not a well-defined set are usually sets outside the scope of mathematics, like the set of the best animals. Right? This isn't a question that the question of what is a best animal isn't well defined. It's subjective at its core. There's no definition for a best animal, right? So this is what the notion of a well-defined set. It's a very important notion that it's often left out when teaching the subject. So some notation. We represent sets with capital letters, right, of the Latin alphabet, just because it's typically the alphabet used for most mathematics or most mathematical texts, along with the Greek alphabet. But elements are written curly braces like I showed here and up above as well. It's just a notation we use to represent a set, and they're separated by commas. So if some element x belongs to some set A, right, we can express the relationship with these symbols, right, where this is the symbol that means belongs to, right? So this element belongs to this collection, this set, right? So not all collections are sets, by the way. Sets have these certain properties, right? Distinct, well-defined. So a set is a collection, but not all sets, not all collections are sets. Right? And so keeping up back with the representations, the mathematical symbols, we simply draw a line through it the symbol belongs to represent the relationship x does not belong to A. And then there's some basic set operations, right? These are very elementary. These are operations, just like you have operations with numbers, and you have different sorts of operations on functions, and you have operations on sets because they're objects, they're mathematical objects. We define these following operations: a union and an intersection between two sets, right? So it doesn't make sense to take to perform these operations on one number. Just in the same way, it doesn't make sense to add a number, just one number. You have to have two different objects, or two objects to add. You can add the same number, but that's different than just adding one number. So in the same way, you need to have two sets to define these operations. Symbolically, a union is represented with this U shape. This intersection is represented with this arc shape. So a union and an intersection, it's a very simple concept. Unions and intersections are sets themselves. So by definition, they are sets. Sets with elements for a union that belong to set A or set B, or both. So really anywhere in set A or set B, or both in set A and set B. Whereas intersection is more specific in this sense, in that it's a set that with elements that belong only to set A and set B. They must be present in both set A and set B to be present in the intersection of set A and B. So a Venn diagram is the easiest way to display this, and Venn diagrams play in nicely with sets. If we can just imagine a set is one of these circles, right? So set A here, set B here, and we have them overlapping. So here, remember the symbol is a union, and we read this as A union B. So A union B would really be, let's shade in what A union B would be. A union B would be all the objects in set A, or all the objects in set B. So it's really the entire Venn diagram. It's really this entire Venn diagram. Now for an intersection, I'm guessing you can already anticipate it's the set that is only contained in this overlapping region, right? So A intersection B would be the set of elements that are present in set A and set B, and nowhere else. Nowhere else can be shaded. And so, just to recap, it's really not a difficult concept to understand. this notion of a set, but it sets up a fundamental basis of learning and understanding mathematics. It's a common ground to understanding and defining mathematical objects. In fact, we can define numbers using sets. We can define functions using sets. So this is a very fundamental concept. And this is often the use of sets. This is often the use of learning what sets are in higher level mathematics or different branches of human inquiry. For example, the example I brought up before, learning formal languages and automata theory, you have to understand what a set is and rigorously define what a language is, a formal language is, what an alphabet is, what a string is. And all these things are sets. They use the concept of a set. So it's important to understand the fundamentals of what a set is, right? And the basics that I've just displayed here that really anybody can understand. It's important to ingrain these in your head. These are the fundamentals we build upon. The set theory is obviously more complex than this, but these are the basis.